Section 5.5 today is about functions involving bases, either exponential bases or logarithmic bases that are not e. So we're not going to be dealing with exponentials, e to the x, and we're not going to be dealing with natural log x, but they will be other bases. So these properties should be familiar to us. Anything to the 0 power is 1. If we have two exponentials with the same base, we would add their exponents together. If we are dividing two exponentials with the same base, we would subtract their exponents. And if we have an exponential raised to the x and we're raising that whole thing to the y, then we would multiply those exponents. So that's a review from algebra. And here we have the definition of a logarithmic base of function of base a. So a logarithm of any other base. Remember, this is basically what we're showing here. This is basically change of base formula. So we're used to seeing this would be changed into log base 10 of x over log base 10 of a. It's the same thing with natural logs, which is basically what they showed there. And then these are also logarithmic properties going between exponential and logarithm. A to the log a cancel, and log base a of a cancels as well. So let's just first start with some algebra and solving for x into these exponential or logarithmic equations. So the first one, if I want to get x out of that exponent, I need to do log base 3 to both sides to get rid of the 3 exponential base. On the left, everything cancels except for the x. On the right, I need to simplify that. I can either use the change of base formula that I briefly talked about on the last page, or we can recognize that 1/81st is the same thing as 3 to the negative 4, and the 3's cancel. I'm left with just the negative 4. If you didn't see that, you could have just done the change of base formula and did log of 1/81st divided by log of 3 on your calculator and gotten that answer. Okay, letter B, to undo a log, we need to exponentiate with that same base. X is 2 to the negative 4th, which is 1/16. Let's do some calculus. Here are our derivative rules. The left side are the rules if it was just x. More realistically, we're going to be over here on the right side, rules 2 and 4, because we generally have some sort of chain rule that we'll have to be dealing with. A to the some sort of exponent other than x, then our formula is natural log a times a to the u, where that stays the same, times the derivative of the exponent. Versus, if it's log base a of u, we do 1 over natural log of a times u, so that's the inside of the log, times the derivative of u. These you do have to know, but you can feel free to just reference them right away until you're more comfortable with them, but we do have to know. I would just, again, stick with that right side because it's more specifically for chain rule questions. And if you get lucky and get a question like letter A here, then we just treat the x like the u, and we would just multiply by 1 in the end, which is the derivative of the exponent there. Okay, so natural log of the base, natural log 2, leaving the exponential part alone, times the derivative of the exponent. That's it. Letter B, natural log of the base, leave the exponential part alone, times the derivative of the exponent. Only other thing I would say is you could put the 3 and the natural log of 2 out front together, and then the exponential second. But that's not an absolutely necessary step. And these last two are logarithms. So in letter C, we're going to do 1 over natural log 10 times the inside, which is cosine, times the derivative of the inside, which is negative sine. So I would probably put that negative sign on top, but I also recognize that if I'm going to have negative sine over cosine, that is tangent. So I have negative tangent over natural log 10. Hopefully you'd recognize that sine over cosine would be tangent, but if you didn't, I would not penalize you. Okay, letter D. I am going to use some logarithmic properties to split this up before taking the derivative, because right now it would be a quotient rule, which is not really something I feel like doing inside of the logarithmic um, derivative properties. So first I'm just going to use my logarithmic properties to split this up. I can bring the 1/2 out to the front from the square root, and then I can take this derivative of each of these terms separately now using property number 4. Okay, so I'm going to have the 1/2, put the 2 in the bottom, natural log of the base times the inside times the derivative of the inside. So that one is set. Second one, 1 over natural log of the base times the inside times the derivative of the inside, which again is just 1. So this one is all set. How much worse would that have been if I have left it alone and tried to take the derivative of that using the quotient rule? That'd be just not very fun. So make sure you do that algebra stuff first and get it out of the way to make your life easier to do the calculus stuff. Okay, integrate an exponential function of a base other than e. So this is the inverse of what we just did, basically. The integral of a to the x dx is 1 over natural log a times a to the x plus c. So the exponential part stays the same. You are occasionally going to have to deal with u substitution, but the straightforward example here, 2 to the x dx, to take the integral of that, it would be 1 over natural log of the base times the exponential as is plus c. Okay, so now we've been dealing with a lot of different exponentials, a lot of different types of functions. How do I know what to do? This is the basic one that we learned right away when we were learning derivatives. X to the number, some sort of number, we would bring that number down to the front and lower it. That's the very basic power rule. But what if our base is a number? Or I'm sorry, what if the base is a function other than just x? So then we just do the chain rule. It's the same exact thing, only du dx is multiplied on the end as the chain rule. So how do I know which power rule to use here? Whether I'm going to use the new exponential stuff, whether I'm going to use what we know before. Let's figure out what we're going to do here. So letter A, take the derivative of e to the e. Well, e to the e is a constant. There's no variable involved in that at all. So the derivative of a constant is 0. Letter B, the derivative of e to the x is just e to the x. That was from a couple sections ago. The derivative of x to the e, this is the power rule that we're talking about here, number 1. We're going to bring that e down and lower it by 1. X to the x, letter D. This one is tricky. I cannot use the power rule because the exponent is not a number. I cannot use our new rules where the base is a number. So I have to do logarithmic differentiation to solve this question. If you don't remember what that is from a couple of sections ago, logarithmic differentiation is when you take the logarithm, natural log, of both sides so that we can bring that x out of the exponent and make this not such a terrible question. I am still going to have to do the product rule here, but it's not impossible. So on the left side, we have 1 over y dy dx. On the right, f g prime plus g f prime 1 plus natural log of x. We're going to multiply both sides by y. I'm obviously not going to leave the variable y in my answer. I'm going to put the original back in. 1 plus natural log x times x to the x. That one is tough. If you don't see it right away, that becomes a really tough problem. Okay, so now we're actually going to just be reviewing some interest formulas. This you should have seen, I feel like, infinite times at this point. You see it in Algebra 1, you see it in Algebra 2, you see it in Pre-Calc, and now we're seeing it again. We're not actually going to do any calculus with this. We are just going to review how to solve for these questions. So to review, P is principal, R is rate in the decimal form, N is the number of times compounded per year, and T is the number of years. Whereas with compounding continuously, there's no N involved, okay? Instead of the 1 plus R over N, we just have E to the RT. Okay, we have $2,500 deposited into an account with an interest rate of 5%. Find the balance at the end of 5 years if it's compounded quarterly. So that's going to be formula number 1, where our quarterly is referring to the number of times compounded. So that's going to be 4. And when I round to 2 decimal places, since this is money, I get approximately that answer. Letter B, we're compounding monthly, so we're still using formula 1 up top for compounding n times per year. This time n is 12. $32.08 and 40 cents. And compounding continuously is formula 2, which is PERT, e to the RT, which is the ideal amount of money we would have, but it's not a realistic situation. There is no bank or investment firm that does compounding continuously because they would lose money. Last question, we have a logistic growth formula that represents a bacterial culture growth, where y is the weight of the culture in grams and t is the time in hours. Find the weight of the culture after 0, 1, 10, and infinite hours. So again, we're not really doing calculus until letter D when we take the limit, but for A, B, and C, we're just plugging in 0, 1, and 10. When t equals 0, y equals 125 over 1 plus all this stuff on the bottom, where we plug in a 0 for t, and that is just comes out as 1 gram. T equals 1, 125 over that garbage, and we get about 1.071 grams. C, when t equals 10. So I'm plugging in 10 for t. 1.244 grams. And last one, actual calculus. What is the limit as t approaches infinity? So infinite limits, I'm going to have to try to think about, I know it's not a real thing, but kind of plugging in infinity for t. What if that t value gets so large? Oh, what would happen to that initial term? This should all be, oh my goodness. I forgot to add that decimal I had on my paper and I did not tell you, so you were probably very confused where I got all those numbers. That should be 1.25 on top every time. Sorry about that. So what if on the bottom here, this was this term went off to infinity. What if e to the negative 4 times a giant number, then that whole entire term is going to go to 0. You have to picture that huge number. If it has a negative exponent, the exponential functions approach 0. So we're going to have to picture that whole term going to 0, and we are approaching 1.25 grams towards infinity. Okay, and that is, let me get down here to the homework, that is our section 5 on bases other than E.